Let's first look at a couple of rules for simplifying radical expressions. First, the product rule for radical expressions says let a and b be real numbers, where the nth root of a and the nth root of b are both defined. Then the nth root of a times the nth root of b equals the nth root of a times b. Now, since this is a rule that has just an equals in between it, it makes it much more powerful. We can use the rule this way, or we can use the rule this way. In other words, if we have two radicals with the same root, we can put them under one radical with the root and multiply the radicands. Or if we have a nth root of some kind of product, we can separate it into two different radicals with the same root. Now, the quotient rule for radical expression says let a and b be real numbers where the nth root of a and the nth root of b are both defined and b is not equal to 0. Then the nth root of a over b equals the nth root of a over the nth root of b. Again, this is another powerful rule because this is only an equal sign. So we can use the rule this way and this way. In other words, if I have the nth root of a over b, I can split it so that I'm taking the nth root of the numerator over the nth root of the denominator. Also, if I have the nth root of a number over the nth root of another number, and the n's are the same, then I can put it under one radical and divide the radicands. Simplify the expression. Assume that all variables are positive. Here we can use the product rule and go ahead and put those under one radical. Now the square root of 1/16 is the same as the square root of 1 over the square root of 16. So we've used the product rule here, and now we've used the quotient rule. The square root of 1 is 1, the square root of 16 is 4. Over here, I have three radicals that I'm multiplying together. I can still use that product rule where I'm putting everything under the same cube root. Now when I multiply the radicands, 2 times 4 times 1 is 8, over 3 times 3 times 3 is 27. Then I can use my quotient rule and break that up as the cube root of 8 over the cube root of 27, and that gives me a 2/3. Let's simplify this radical. The square root of x squared is x, the square root of 81 is 9. If you don't want to specifically write out the square root of x squared over the square root of 81 and you want to just do that in your head, that's fine. Over here I have the square root of x squared over 16. Again, I don't need to specifically write that out. I can go ahead and just take the square root of the top and the square root of the bottom and get x over 4. Square root of 45 over 5. Well, it's a good thing we can use the quotient rule backwards because I can't take the square root of 45 and have it come out to be a nice number. I can't take the square root of 5 and have it come out as a nice number. But I can put them all under the same radical since they're both square roots. Now I know that 45 divided by 5 is 9. Then the square root of 9 is 3. Here I have two radicals multiplying. I can go ahead and put them under the same cube root. Negative 4 times a negative 16 is a positive 64. Now the cube root of 64 is 4. Here, the fourth root of 9 times the fourth root of 9 is the fourth root of 81, which we know is 3. If you'd like, you can use your calculator. Here I have a problem. I have something that doesn't have a square. It's not going to be able to come out. And the same thing down here. So it's a good thing we have that quotient rule, because I can put them all under the same square root and simplify that radicand. Now I'm going to cancel those x's, and that gives me a square root of 4y squared, which we know is 2y. The cube root of negative 8y cubed. So here, first the cube root of a negative is going to be a negative number. The cube root of 8 is 2, and the cube root of y cubed is y. Now simplifying radicals in nth roots. First, we want to rewrite the radical with prime factorization of the radicand. Then we'll separate the radical using the product rule by placing the largest perfect nth powers of the radicand in one radical and the leftovers in the other radical. Then we'll simplify the perfect nth powers radical. Let's demonstrate this step-by-step process with this problem. We'll simplify the radical expression by factoring out the largest perfect nth power. Then we'll assume that all variables are positive. Our first step was to rewrite the radical with prime factorization of the radicand. That's already been done for us. Step 2 is to separate the radical. We're going to place two radicals, both of them cube roots, and we'll put our perfect nth power factors here and all the leftovers in the second radical. So in other words, anything that goes in here needs to have an exponent that is a multiple of n, a multiple of 3. So when I look at negative 5 and a to the 6th, I can put a to the 6th here, because 6 is a multiple of 3. That takes care of all of my a's. My negative 5, well, I'm not going to have enough to take care of that, so I'm going to go ahead and just put the 5 here. And I know that when I take the cube root of a negative, it's going to be negative, so I'll go ahead and place the negative sign in front there. Now, I simplify the perfect nth powers radical. So I have my negative, and the cube root of a to the 6th is a squared. The cube root of 5 is just going to stay. You'll have to be very careful the way you write these so that that cube root is in the hook of that radical, so that it doesn't look like it's a to the 23rd power. Now let's simplify this one. First, we want to get this all into the prime factors. So I have fourth root of, I know that 16 is 4 times 4. Each of those are 2 times 2. So 16 is 2 to the 4th, then I have x to the 4th, then I have y. Then I'll break up into two separate fourth roots. For the first one, I want to put my perfect nth powers, or my perfect fourth powers. Every number in here needs to have an exponent that is a multiple of 4. So I have 2 to the 4th, that would fit perfectly here. I have x to the 4th, that would also fit perfectly there. Then I have a y. It doesn't have enough to stay into the perfect radical, so we'll put it in the leftover radical. Now I simplify my perfect radical. So the fourth root of 2 to the 4th is 2. The fourth root of x to the 4th is x. And then I have my leftover radical of the fourth root of y. Now the square root of 6x to the 5th times the square root of 6x. I need to first go ahead and multiply those. So I have 36x to the 6th. Well, I know that 36 is a perfect square and x to the 6th is a perfect square. So I can go ahead and just take the square root of that and not break it up into the perfect nth power and the leftover nth power radicals. Square root of 16 x to the fourth y to the sixth. Again, I can go ahead and just take the square root of this. I know the square root of 16 is 4. The square root of x to the fourth is x squared. The square root of y to the sixth is y cubed. Simplifying the square root of 200. First, we want to break up 200 into its prime factors. It's 2 times 100. 100 is 2 times 50. 50 is 2 times 25. 25 is 5 times 5. So, square root of 200 is the square root of 2 cubed 5 squared. That gives me the square root of, well, how many 2's can I fit here? I'll be able to put at least 2 of them there and 1 in the leftover. Then I'll put a 5 squared under there, and there's no more 5's to put in the leftovers. So when I take the first radical and simplify it, I have 2 times 5, and then I have my leftover radical, and that gives me 10 square roots of 2. The square root of b to the fifth. Here, I'm going to break up my b to the fifth into perfect nth powers and the leftovers. So first of all, my n is 2. I need to take out the largest multiple of 2 from exponents here and put them into this radical. So I'm looking at b to the fifth. The largest multiple of 2 that can come out of 5 is 4. So I'm going to put b to the fourth there, and my leftover in the leftover radical. That gives me the square root of b to the fourth is b squared, and my leftover radical of square root b. The square root of 8n cubed. Again, let's go ahead and write this in its prime factors. 8 we know is 2 cubed, and then we have the n cubed. We're going to break it into the perfect square root and the leftover square root. And under the perfect square root, I have 3 2's, so I can go ahead and put 2 of them here and 1 in the leftover. N cubed, I can put 2 of them here and 1 in my leftover. Then when I simplify my perfect square root, then I have 2n and then my leftover of square root 2n. Square root of 12a squared b to the fifth. Again, let's come over here and find the prime factorization of 12. That gives me the square root of 2 squared times 3a squared b to the fifth. Now break up into your perfect square root and your leftover square root. In the perfect, we can put 2 squared. We don't have enough of 3, so we put that in the leftover. A squared we can put in here. And with b to the fifth, I can put 4 of them here and 1 here. Now, why wouldn't I just put a b squared in the first one and then put b cubed here, so that this is a 2 just like the index? Well, we could simplify that, and then this comes down, and we end up with an exponent inside the radical that is greater than or equal to the index. So that shows us that this radical is not simplified. We definitely need to put as many of the b's into that first radical as possible. So that's why we're putting 4 there and just 1 there. When I take the square root of this, I have 2ab squared, and my second radical, 3b. cube root of negative 125 x to the fourth y to the fifth. Well, my 125 is 5 times 25, and 25 is 5 times 5. So first I know that when I'm taking the cube root of a negative, I'll end up with a negative. And let's break up our radical into a perfect cube root and the leftover cube root. I know I have 3 5s, so I'll put 3 of them in the first one. X to the fourth, I can put 3 x's there and 1 in the leftover. Y to the fifth, I can put 3 y's in the first and 2 y's in the second. That gives me a negative 5x y cube root of xy squared. In this problem, we have quite a bit going on. First, we'll probably want to go ahead and multiply those radicals so that we get everything under one radical, and then we can separate it again. So I have a square root of 7 squared a cubed all over. I know that 27 is 3 cubed times another 3 is 3 to the fourth. Now I'm clear on these. They already have exponents that are multiples of that index 2. What I need to do is separate out an a. So I'm going to put in this first one, 7 squared a squared over 3 to the fourth, and multiply that by the second radical of just square root of a. Now when you write a radical over a fraction, make sure that your radical hook goes all the way down so that you can be sure that the reader sees that your radical is covering the whole fraction and not just the numerator over a 3 to the fourth. Now when I simplify this radical, I'll have a 7a over 3 squared times my square root of a leftover radical. And simplifying, I get 7a over 9 square root of a. In this lesson, we'll be adding, subtracting, multiplying, and dividing radical expressions. If possible, simplify the expression. Assume that all variables are positive. 2 square roots of 3 plus 7 square roots of 3. You can add these radicals, since they're like radicals, the same way as we would add something like 2x plus 7x. So what we have is 2 of these radicals plus 7 more of those radicals gives us 9 of the same radical. Here I have again like radicals. 4 cube roots of 5 plus 2 cube roots of 5 is 6 cube roots of 5. So we must have like radicals in order to add or subtract. For them to be like radicals, they have to have the same index and the same radicand. Square root of 2 plus the square root of 18 minus the square root of 32. This problem at first seems that we can't do anything because we have unlike radicals. But you'll notice these two radicals are not simplified. We first need to simplify those radicals, and then we'll see if we have any like radicals to combine. So first with 18, 18 is 2 times 9, 9 is 3 times 3. With 32, it's 2 times 16, 2 times 8, 2 times 4, 2 times 2. So this problem is the square root of 2 plus the square root of 3 squared times the square root of 2 minus the square root of 2 to the fourth times the square root of 2. That gives me the square root of 2 plus the square root of 3 squared is 3 square roots of 2 minus the square root of 2 to the 4th is 2 squared, which we know is 4 square roots of 2. Now we have 3 radicals that are alike, and we can put them together. 1 square root of 2 plus 3 square roots of 2 is 4 square roots of 2, minus 4 square roots of 2 is 0. The 4th root of 48 plus 4 times the 4th root of 3. Again, it looks like we have unlike radicals and cannot perform this operation, but we need to simplify the 4th root of 48 first. So we'll take our 48 and separate it into its prime factors. And then we can break that radical up into perfect fourth powers and its leftover fourth powers. So we have 1, 2, 3, 4 2's and a 3 that's left over, plus our 4 fourth root of 3. So with this step, we've simply broken this into this and copied down 4 times the 4th root of 3. So here the 4th root of 2 to the 4th is 2 times the 4th root of 3 plus 4 4th root of 3. Then when I add those together, I have 6 4th root of 3. Again, with this problem, I need to first simplify my radicals and then determine if I have like radicals to be able to add. So my 8k, I know I'll be able to break that up as the square root of 2 squared, and then my leftover will be another 2 and the k. So the 8 is 2 cubed. I put 2 of them here and 1 here. We only have 1k, so it goes into the leftover radical. Now we're ready to separate this. So we have 2 square roots. 18 is 2 times 3 times 3. So I can put 2 3's here, and the 2 has to go there. K has to go in the leftover. Now I'm ready to simplify further. I get 3 square root of 2k plus the square root of 2 squared is 2 square root of 2k plus the square root of 3 squared is 3 square root of 2k. Now when I add these up, I'll have 3 of those roots plus 2 more of those roots plus 3 more of those roots gives me 8 square root of 2k. The square root of 25x cubed minus the square root of x cubed. First we need to simplify both radicals. This may look simplified, but remember the exponent is greater than or equal to the index, so we know that it's not simplified. So I'll break up both of those radicals. That gives me 25 is 5 squared. X cubed can be broken up as x squared and x in the leftover radical. Then x cubed is x squared and x in the leftover. Now simplifying the first, I have 5x square root of x minus x square root of x. Now I have like radicals. I also have like terms. I have a 5x and a negative 1x, so like terms and like radicals. So I have 5x radicals minus 1x radicals gives me 4x of those radicals. 15 square root of 8 over 4 minus 2 square root of 2 over 5. We have a dual problem here. We first need to simplify this radical, And then we're subtracting fractions. Remember that we'll need to have common denominator in order to subtract. So first things first, let's simplify this radical. I have 15 square root of 2 squared square root of 2, because 8 is 2 cubed, all over 4, minus my 2 square roots of 2 over 5. That gives me, for my first radical, 15 times 2 times the square root of 2 all over 4 minus 2 square roots of 2 over 5. That gives me a 30 square root of 2 over 4 minus 2 square roots of 2 over 5. Now to get a common denominator. Looking at 4 and 5, the least common denominator is going to be 20. So I'll need to multiply this radical by 5 over 5 and this radical by 4 over 4. So this gives me a 5 times 30 is 150 square roots of 2 over 20 minus 4 times 2 is 8 square roots of 2 over 20. Now I have a common denominator. I have like radicals on the top, so I can go ahead and subtract. I get 142 square roots of 2 over 20. Now I see that this and this, they're both even. So I can go ahead and take a factor of 2 out of them. So I have 2 goes into 20 10 times, 2 goes in 142 71 times. So that gives me a 71 square roots of 2 over 10 as my final answer.